All right, atomic history, part 2. Here we go. You ready? This should be a little quicker. Our list, got our list. This is for this Wednesday list, okay? Get your list, doggone it. Have the list. Well, I have several other names on here we have to go through. I've got Thomson, Millikan, Rutherford, Chadwick. You know, what did they do? What did they contribute? All right, let's start out with Thomson. Now, at this point, we now have an atomic theory that John Dalton developed, okay? He was right on most of the stuff. Good stuff. Just a quick review. We also, on this list, you have this, A over ZX. And what that means, see it's right there, A over ZX. And then I have isotopes behind it. I've already taught you this, so we've done this. That is the way of writing an element. So X means the symbol for the element, hydrogen. And A means the atomic mass. And Z, that's a Z. And down here means the atomic number. So we've gone over that already. And this would be deuterium. It would have a mass of 2, number 1. This is why it's hydrogen. And it would have 1 neutron when we subtract those. Okay, quick review. And isotopes, we went over those different kinds of the same atom because of different amounts of neutrons. Yes, different amounts of neutrons. Very good. Very good, Wilma. All right, next guy. Now we get to the late 1800s. So finally, the atom itself, now we've had this idea of the atom around for a couple thousand years with Democritus. And so now we have the atom and it is found to be broken down. So that's one other point that Dalton did make. In that first point, he said everything is made up of atoms, which was correct. But there was actually a second part that he had added to it, that atoms are indivisible with liberty and justice for all. He assumed that atoms were it. There was the smallest part, and he was actually wrong about that. So for part 1, that second part, I didn't write it in because I didn't want to, I felt bad about himself already for missing part 2 about all atoms are identical of the same kind. He said that atoms cannot be broken down. So he was wrong about that. So kind of for that first point, he was half right, half wrong. Everything's made up of atoms, but atoms can be broken down. As we now know, you know that. You know that atoms are made up of protons, neutrons, and electrons. You do. And those protons, neutrons, and electrons can be further broken down into quarks and all kinds of different things. And many different kinds of quarks. That's atomic stuff, so we won't get into it. But the protons, neutrons, electrons, we do need to know. And it was in the late 1800s, okay, late 1800s, Thomson, first guy on that little list there, Thomson discovered the electron. J.J. Thompson, J.J., cool name, J.J. It's not J.J. J.J. Thompson. So late 1800s, Thomson discovers the electron. He's the electron guy, all right? The electron guy. So Thomson was followed by Millikan. Oh, well, actually, first I'll just talk a little bit about Thomson. When he discovered the electron, he did it using an electron beam with magnets. He discovered that the electron beam was deflected by magnets, which, I don't want to get into this too much, but magnets have positive and negative properties to them, so it was deflection due to the magnets. So he said to himself, the electrons must have some kind of charge to them. They must be either positive or negative charge. And the concept of charge, positive and negative charge, was known at that time. So he went, you know what? I discovered it. I'm making the call. I am J.J. Thompson. Who's going to mess with me? Answer, no one. Okay? And he said, I am going to give the electron a negative charge. So the electron is given a negative charge because Thomson, the discoverer of the electron, said it was going to be negative. Now, he could have said, I'm giving the electron a positive charge. Because nature doesn't care. Nature does what nature does. It doesn't care what you designate as being positive or negative. It's not going to make any difference. If the electron were given a positive charge, the proton would be given a negative charge, and it wouldn't change anything. Everything would still work the same way. Chemistry would still do what it does. We would just be saying that the electron has a positive charge instead of a negative. But Thomson said, I discovered it, I'm calling it. He gave it the negative charge. So negative. Boom. All right, next. Along comes Millikan, Milkman. Millikan, okay, our next guy here on our list, Millikan, he says, actually what he did, just not that long afterwards, it was 10, maybe 15 years after Thomson discovers the electron, he came up with what's called the mass to charge ratio, mass to charge ratio. And he determined that each electron has a 1 unit of negative charge. So each electron, so not 2 units of negative charge, not 3, 1. Every electron, so Millikan mass to charge ratio. So he was a charge mass guy when it comes to the electron. He determines that each electron gets a negative charge. And sometimes you'll see the E with a negative up there, meaning it has one negative charge associated with it. And also the mass ratio, meaning that he did an experiment that determined that the mass of the electron is really, really small compared, we talked about this in the last video, really small compared to the neutrons and the protons. And in fact, the mass, he didn't come up with an exact mass of it. Okay, that wasn't possible in the early 1900s, but he came up with a relative mass of the electron as being 1/1800-ish. A little bit more than that, it was like 1/1840, but we'll say 1/1800th the mass of a proton or a neutron. So in other words, compared to a proton or a neutron, it's really, really tiny. You would need 1,800 or 1,800 of them in order to make the mass of just one proton. That's why we give it a relative mass of 0. It does have mass, but a relative mass of 0 because it's so small. Okay, that was Millikan. Next, I had the term on the sheet, radioactivity. I'm not going to go through radioactivity. We really don't need to know it, but it does tie in to the next guy, who is Rutherford. Rutherford, now we're World War I-ish, still early 1900s, he determined that the proton is positive and that the atom is mostly empty space. So he determined it by using what's called the gold foil experiment. I'll give you a real quick breakdown of the gold foil experiment. What he did, he used a radioactive material which gave off alpha particles. An alpha particle, that's why I put radioactivity down. An alpha particle is a kind of radiation, and an alpha particle is a positive particle. And so his source gave off these positive particles, fired them out in a beam. And he has some gold foil here. And behind it, he put some film. It was known at the time that radiation will expose film. And so now, if we have these radioactive positive charge alpha particles, radiation, moving through the gold foil, hitting the gold foil, he wanted to see if any of these positive particles can get through his layer of gold foil. And remember, we talked about gold earlier in the last unit of matter. We said gold is extremely dense, one of the most dense substances on the planet. So he figured that if he fired these positive alpha particles at the gold foil, they wouldn't get through because gold is so dense. So fire them, nothing's going to happen to his film, his photographic paper back here. Not going to get exposed because none of the radiation will get through. Sounds good? Great, let's try it. Wrong, so very wrong. Wrong. Now, he discovered that the vast majority of particles, these alpha particles will go right through that very dense gold. And they exposed the photographic paper in the back. The vast majority of them went right through, like Swiss cheese. What else he discovered was on occasion, some of these alpha particles would be deflected. Would be deflected off at some angle. And you can determine this by putting more photographic paper around it. And every once in a while, the photographic paper gets exposed in a spot or two here or there. So that meant that some of these particles must have gotten deflected away from the gold foil. So he came up with two important things about the atom with this. One, these are positive particles. They got deflected. That means the nuclei of this gold must not like those positive particles. It's a natural fact, opposites attract. Paul Abdul, 1992, I think. Yeah, a little cat video there. But opposites attract, but like charges repel each other. So if I got a positive, and I'm sitting here, I'm in a positive particle, and I'm in one of the nucleus. I'm in a nucleus of the atom of gold, and here comes this positive particle, this alpha particle. I'm positive, you're positive. Are you sure I'm positive? Are you sure I'm positive? Okay. And so I'm going to get near you. You're going to go, no, get away from me, no. Okay, here comes no, get away from me, no. that would cause deflection. These things are not going to, because they don't like each other. They want to go away. So some of those did that. They told him that the nuclei of the atoms must be positive. That's why we now know that the protons are in the nucleus of the atom. Electrons are on the outside. Okay. The other thing we also found out is that the vast majority of these particles go right through this very dense lead, so therefore these particles here, although very dense, most of what's there is empty space. If these positive particles, which don't like the nuclei, go right through, the vast majority of them, they just go right through. So you might have down here, you might have a nucleus here, but there's all this empty space in between. So these alpha particles, for the most part, go right through. So that means that even something as dense as lead has a lot of empty space. So atoms, and the model that's usually taught to students is, if I have a tennis ball, not just a tennis ball, check it out. Can you see that? SpongeBob tennis ball. Yeah, you're jelly. Yeah, you are. SpongeBob tennis ball. I got one. You don't. Okay. Tennis ball represents the proton of the hydrogen atom. The one electron would be about a mile away. And they'd be the size of a grain of sand, by the way. Grain of sand a mile away. That's a lot of empty space. So atoms are mostly empty space. You and I are made of atoms. We're mostly empty space. See? You can just see right through me. See? I'm mostly empty. You can see right through. Yeah. Okay. So that's what we got from Rutherford's experiment. Okay. Now what we know? We know the electron is negative. We know that each electron gets a one negative charge associated with it. It's very light. Doesn't have a lot of mass to it. We know the protons are in the nuclei, and they are positively charged. Whew. Okay, last guy on this list is Chadwick. Chadwick discovered the neutron. It was until the 1930s that Chadwick discovered the neutron. So he's the neutron guy. So that last particle of the atom to complete our puzzle of our general atom. Electrons first, protons second, Chadwick neutron third. Why did it take so long to discover the neutron? Think about it. Neutron, neutral. It didn't have a charge associated with it. The two experiments that Thomson and Rutherford set up, they had an effect on the positive and negative charged particles. They were deflected, and so we can figure, though those were found first, the neutron took a little doing. If you ever want to figure out, go look up Chadwick, how we discovered the neutron. Pretty sweet. But he's the neutron guy. 1930s, finally now we have a little bit more of our atomic picture now complete. All right, that is History of the Atom, round 2. Whew. One thing I had that pair because I'm exhausted.